Yeah. Well, all right. Very happy to see everybody here at Bangkok. I'm Wishlonger, the co-founder of Pharos, and we are Pharos. We are going to talk about what we are doing to scale to over 1 billion users with a blockchain infra. So first, let me introduce Pharos. We are a new EVM-compatible Layer 1 blockchain, and with a unique full-stack parallel technologies across the consensus, execution, and storage. And we're aiming to support over 1 billion users to bridge the existing fintech services with Web3 innovations. To achieve this goal, we need to have very extreme performance. So more specifically, we're talking about 2 gigagas per second. That is 50K TPS. It's not a single node performance, but a full-fledged network. And we have a 1 second finality, and we must scale to 1 billion accounts and over 100 terabytes of data, and with a very minimal standard hardware and without downgrading on the performance. So how we can do that to achieve this high-performance blockchain, and that is our full-stack parallel technologies in storage and execution, and also in consensus. So first, let me introduce the Pharos store. It's the world's first blockchain-native storage system. So basically, as advancing of the blockchain performance, many have realized that the storage become the bottleneck towards a high-performance blockchain. So there are like two kind of challenges in the existing blockchain storage. One is like the data size of the blockchain is consistently growing. For example, here, like today, in the Ethereum mainnet, there are around 287 million accounts, unique accounts. And for archive node, it requires 19 terabytes of data. And what's worse is that the storage performance is really poor. And in the bottom of the figure, we have tested and have this time breakdown on the Go client of the Ethereum. You can see that almost 52% of the transaction processing time is spent related to the blockchain I/O. So to understand why is this, we maybe need to go quite deeper into the design of the storage. So basically, the traditional blockchain storage, it has a 2-layer design. So we have a authenticated data structure. Usually, it's a Merkle tree above, and we have a KV database. Usually, it's RocksDB or LevelDB on the bottom. So this will cause 3 problems. The first one is called long I/O path problem. So imagine we want to update the balance of Alice. We need to first go traverse the Merkle tree from the root node to the leaf node. And again, for each node, we need to find its hash and traverse again in the LSM tree in the database. So the number of I/O is polynomial to the size of those 2 trees. And we have tested that in the Ethereum that when we want to access global states, and usually it takes around average of over 100 I/Os on the disk. And the second problem is called hash-based addressing. So we know all data on the blockchain is indexed by a hash as a key, and they are randomly located in the disk. And the disk is only optimized to handle a large chunk of data instead of randomly located small files. So this is a really poor performance if we have this hash-based addressing. And the third one is state bloat. It's not only because that the data is persistent in the blockchain and will continue to grow. And what's worse is that we need to, whenever a node is updated, the whole path in the Merkle tree need to store redundantly in the storage. And this will cause the storage to bloat very quickly. So basically what we do in Pharos, and we systematically, completely redesigned the blockchain storage. And generally we use three techniques here. The one is we call it MPT pushdown. We integrated the Merkle tree directly inside a database so that each of the Merkle tree node only require don't only record the hash, but the direct location of the data in the storage, so that we eliminated the long I/O path problem in the traditional storage architecture. So the second one is we use a version addressing. So basically, it means that all the data are indexed by the block number. So it's not by the so all the data can be packed and aligned by pages in the disk instead of randomly located in the disk, so that we eliminated the hash-based addressing problem. And the third one is we use a delta encoding techniques to only record the modified part of the storage instead of the redundant data of all the paths. So using this, we have developed the first blockchain native storage. So what eventually we can get. So we have evaluated using by replacing the storage component of the Go client of Ethereum, the gas, and immediately we see that we have achieved around 60 times higher throughput in the I/O and over 10 times faster in the state sync. And what's more important, we saved 80% of the storage cost. We only use 1/5 of the storage to store all the data, and that's what we get. And we also do a stressful test, and we can say that in the right-hand side that the Pharos store will maintain at 4,000 TPS all the time, even the number of the addresses exceeded 1.6 billion, and the data exceeded over 100 terabytes. That is a Pharos store. And next is what we have innovation on our execution. So we have this new compute model for the Web3. Basically, with this we can have a precise transaction level and a block level parallelism to maximum the utilization of the CPU resources. And we have this, we call it Dora compiler and the Dora VM. We have designed the unified IR so that the compiler could compile both the EVM bytecode and the Watson bytecode into that unified IR. And in this IR, we can do AOT and IoT to generate deep optimize the native module to execute it by the Dora VM. And we also enabled a very good interoperability between this Watson contract and the Solidity contract to enable more innovative applications on the network. So the Dora is now open sourced for all, and we have also tested compared with other execution engine. Generally, we can achieve 40 times better performance than the REVM and about 2 times better than the RGMC. So, and we welcome everybody that can take a look at our open source repository and contribute to that project. So the next is consensus. So generally, we have a ultra high throughput, low latency, asynchronized BFT algorithm. So in this algorithm, we allow all validators to propose the block simultaneously so that to maximize the usage of the network bandwidth. And at the same time, we avoid the single point failure because all nodes can propose the block at the same time. So we also we compare that with the well-known other consensus algorithm, for example, the hot stop and the task. So compared with the hot stop, we have over 10 times higher throughput on the consensus algorithm. And also on the task, we have like over 3 times higher throughput. And this result has actually published in the SOSP conference we had in the last year. So yeah, I think that's all for today. And you're welcome to, like, if you want to know more about Pharos, you're welcome to visit our website and Twitter. We have tons of the detailed articles about those full parallel technologies. And you are also welcome to join our Discord channel to discuss with our dev team. Yeah, thank you. All have fun.